name is Nikita. I work at JetBrains on, oh wow, now the sound is better. Yeah, I work at JetBrains on multiple products related to concurrent programming. So in short, I work on Kotlin language. So I designed synchronization communication primitives for Kotlin coroutines. I also lead a framework for testing concurrency on JVM and periodically do some research. So I'm somewhere in between the industry and the academia. And today we are going to discuss the framework we develop at JetBrains for testing concurrent data structures. So I hope you all are, in some sense, interested in concurrent programming, but also want to know some other things about you. So is there anyone who is familiar with Kotlin? So half of you. Wow, I thought most of you are familiar with Kotlin. So if you
Just have heard of Kant.
you tried to write something. So, but even if you program in Kotlin every day or you just heard of it, I think you've heard of Kotlin coroutines. And in Kotlin coroutines, there are a lot of concurrent primitives under the hood. The coroutine dispatcher that schedules coroutines on threads, maintaining per-thread queues and global queues, which are a little bit specific. Channels, rendezvous, buffered, conflated, many of them that coroutines use for communication. Finally, there are mutex semaphore synchronization primitives. And all these primitives play a key role in the Kotlin coroutines implementation. And we need to ensure that these primitives are correct. So that's why we have a specific framework for testing such concurrent primitives to ensure that when you use them, you don't face any concurrency-related problems. And the framework that we use is called Lincheck. So it's open sourced. It's available on GitHub. You can use this QR code in the corner to go to the GitHub page. But before we go into the framework discussion, let's write a concurrent algorithm that we are going to test. So you might ask, Nikita, what should I do to develop a new concurrent algorithm? So glad you asked. Well, a couple of years ago, I would say that you need to read a lot of books on concurrent programming. You need to read popular papers published at top conferences. You need to implement many of the algorithms, thus building the intuition, getting to know the techniques that are used when developing algorithms. And then, when you have all this intuition, when you know these techniques, you can create something new. But, you know, that sounds so ancient, right? So nowadays, we tend to write code differently. So we have this well-trained guy who already read all these books, all these papers, and we can use this guy to develop an algorithm for us, right? Let's give it a chance. So let's ask the AI systems to implement something that is easy to understand, but is still non-trivial. For example, a concurrent bounded queue. So bounded queue is a queue of limited capacity. So when the queue is full and you call offer, then this offer doesn't return the element and returns false. But the poll operation, it works similarly to the to a regular queue. It extracts the first element from the queue or returns null if this queue is empty. So this is just a queue of bounded capacity. And we want to implement a concurrent bounded queue based, of course, on the primitives that we have in the standard library. So we're here at the Java conference. Let's use the Java standard library. So here I ask the AI assistant to implement an unblocking bounded queue based on Java's concurrent linked DAG. And of course, we want to keep the code simple with some comments. And here's what it produced. I don't expect you to read this. I refactored it a little bit for you, and we'll present on the next slides. But this is the code that ChatGPT produced yesterday. Okay? So that's the concurrent bounded queue by ChatGPT with the specific capacity. And to store the elements, it uses a concurrent linked DAG queue data structure. So this is a concurrent queue from the standard library. And to maintain the current size of the queue to the number of elements in the queue, here we use an atomic count. So to add a new element, the algorithm first checks the size, and if the size is equals to the capacity or is greater than, we say, no, the queue is already full. So we return false. We don't insert the element. Otherwise, we insert the element into the underlying queue and increment the counter. So the poll operation, it first checks the underlying queue. And when checking this underlying queue, tries to extract the element from this underlying queue. If there is an element, there was an element, we decrement the count and finish. Otherwise, we return null. So who thinks that this implementation is correct? Who thinks it's not? Most fair, you don't trust ChatGPT. Me neither. But, okay. But when we ask ourselves whether this implementation is correct, we first of all need to decide what do we expect by correctness. And if we live in the sequential world, then we do know the queue semantics, and we can easily reason about the reason whether the specific execution is correct or not. For example, here we create a bounded queue of capacity 2, insert 2 elements, and then the following offer attempt fails. And after that, we extract the first element. Who thinks this execution is correct? Who thinks it's not? So everybody agrees that it's correct. Yeah, because the queue capacity is 2, so the third offer should fail, and here we extract the first element, thus following the first in, first out queue semantics. So everything is fine here. But if we take a look at this example, when we have when the last offer succeeds, then it's incorrect, right? Because in this case, the queue capacity exceeds, and this violates the bounded queue semantics. So in the sequential world, everything is simple. We know the semantics, we take a look at the execution, and we can easily decide whether it's correct or not. But what about the concurrent world? What do we expect from concurrent data structure when these concurrent operations may interleave in many different ways? And when saying that concurrent data structure is correct, or atomic, or thread safe, we usually mean linearizability. So this is the default correctness condition for concurrent objects. And in short, we call an execution linearizable if we can express it with a sequential execution that doesn't violate the happens before order between these operations. So it doesn't violate the program order and the synchronization between threads, and shows the same results. So when we can show that all the possible executions are linearizable, then we say that the data structure itself is linearizable. Okay, I understand that it's a little bit unclear how to use this definition, so let's try to understand it with examples. So I've prepared several examples, and we'll try to analyze whether the executions are linearizable or not, whether they're correct or not. So in this example, we have a queue of capacity 2 and 2 threads. In the first thread, we insert element 1 and then extract it. In the second thread, we insert 2 and extract it. Is this execution correct? Can we find a sequential execution that doesn't violate the happens before order and produces the same results? So who thinks it's correct? Who thinks it's incorrect? Okay, so let's try to find such a sequential execution. And we can easily construct one. So we can say that first, the operations in the first thread were executed. Then the execution switched to the second thread. And then the operations from the second thread were executed. So we do not violate any synchronization between threads, because there is no synchronization between threads, and we do not violate the program order. So we found a sequential execution that can explain these results. Okay? Okay, let's take a look at another example. Now the difference is that in the first thread, the poll operation extracts 2, but in the second thread, it extracts 1. Is this execution correct? Who thinks it's not? Anyone? Okay. So yeah, indeed, it's also correct because we again can find a sequential execution that explains these results, right? So we can start with the first thread, inserting 1 into the queue, then we switch to the second thread, we insert 2, then we extract 1, we go back to the first thread, we extract 2. That's how we can explain these results. Okay, a couple of more examples. Now we have an additional offer in the second thread. Can we now find an execution, a sequential execution that explains these results? Let's think a little bit. So who thinks we can? Who disagrees? Aha, so some people think that it's impossible. Maybe you're right, but let's try to construct one. So here we still can do that. Now we can start with the second thread, inserting 2 into the queue. Then we go to the first thread. We insert 1 and extract the first element. The first element now is 2 that we added in the second thread. Then we go back to the second thread. Since we have only 1 element, we can successfully add 1 more element. That's what we do now. And extract 1. So,
shouldn't the offer 3 return false in capacities 2?
So the question is, should the offer 3 in the second thread return false? But you see here, so we start with the second thread. We add 1 element, then we add 1 element in the first thread, and then we extract 1 element. So before we call offer 3, we have only one element in the queue. The queue capacity is 2, so we can successfully add one more element. So that's why this offer 3 succeeds. Okay. But is this one also correct? So now the difference is that the last poll in the second thread, it returns not 1 but 3. Let's try to find such an execution. So we're gonna stay here until we find it. It is possible. So who thinks it's possible? So 1, 2. Who thinks it's not possible? No, we have democracy here. So no, it's incorrect, and we can explain why. Because now we cannot find such an execution, and we need to show why we can't find it, right? And I don't remember why. All right. I think I can explain. Okay, so you see that this poll, it should return 3, and the queue capacity is only 2. Okay, so before this poll, we have 2 offers. We add 2 and we add 3, and then we extract 3. So we extract the second element. To extract the second element, before calling this poll, we should call poll from the first thread. Otherwise, there is no way to extract the second element. But if we call poll before that, then before calling poll, we add one more element. So, what is the problem here? Yeah. So the problem is that the only way to extract 3 is to start with the second thread, adding these 2 elements, and then to call poll from the first thread. But in this case, the offer in this first thread, it should return false because the queue capacity is 2. We already have 2 elements added in the second thread. So this offer should return false. It should fail. But it doesn't here. And since it doesn't, we cannot find such a sequential execution that will explain these results. And if we can't find such an execution, then we say that it's not linearizable. Okay? All right, so if you have questions here, I think it's good time to ask them. So maybe one question. Anyone? No one. Good. So, I hope with these examples you now better understand what immutability means and what we usually want from concurrent data structures. But here's a question. How can we test our data structure for immutability? And usually when programmers need to test concurrent data structure, they write a complex stress test. And these stress tests are often non-deterministic, so sometimes they flack. They cover only easy to verify scenarios, like you have 2 threads, you call enqueus in one, you add elements in one thread, you retrieve elements in another one, then you check some simple conditions. And also these tests, they usually contain a lot of technical code that is not related to the logic we want to test. And okay, let's say we have a very good stress test. A really cool one, so we cover a lot of different scenarios, so we can find bugs, and we've got a bug. But what's going to happen after that? So we have a bug that occurred likely after calling 100 or 1,000 of operations. So we have such an execution, and we need to analyze it. And usually to do that, we ignore the test. We just read the code over and over, over and over, and over and over, until we realize why this situation occurred. So with the typical stress tests, it's really hard to understand the root cause of the problem. And ideally, we need some framework that will help us to write concurrent tests that can make these tests reliable and also help us to investigate the bugs it detected. And let's try to come up with an ideal test. That's how I want this test to be. So, like, I have a test class, then I say, I want to test my bounded queue implementation. Let's just say with capacity equals 2. I want to test offer and poll operations, and then run just some magic button and say, test it. And then I want this run concurrent test to tell me whether this implementation is correct or not. Do you want such a framework? I do, because I program a lot of concurrent code, and without such a framework, without a declarative way of writing concurrent tests, it's really hard to verify implementations for correctness. And that's exactly what the Lincheck framework that we developed at JetBrains does. The only difference is that instead of this run concurrent test, it has a slightly different API to configure the test. And when we run this code, Lincheck will stress test the declarative operations and report an error if detected. So let's run this test. So if we run this test to verify the bounded queue implementation produced by the AI system, then this test fails. And here Lincheck found a scenario in which the data structure worked incorrectly. So here we observe two offer calls in the first thread and one offer in the second thread, and all of them succeed. So we have a queue of capacity 2, but all these offers have succeeded, so it's obviously incorrect, right? Because the capacity has exceeded. One of these offers must have failed, but it didn't. Here's the question. How has Lincheck found the error? And I want to briefly explain how Lincheck works. So in the test, we declare the operations on the tested data structure, and Lincheck takes these operations and uses them to generate many concurrent scenarios, putting these operations randomly into multiple threads and generating arguments when needed. After that, it runs each scenario many times, hoping to observe buggy behavior. And when an unexpected exception, for example, is detected in one of the operations, it's easy to say, hey, we just got a bug. We can report it. But in general, the execution completes successfully with some results. And we need to verify whether these results are correct or not. So that is the last phase. And Lincheck automatically verifies whether the results are correct or not. So it tries to explain the so do you remember what linearizability is? So we just discussed, right? So when you say that the data structure is linearizable, we mean that the execution is linearizable. We mean that we can find a sequential execution that can explain these results. That's actually what Lincheck does to understand whether the results are correct or not. It tries to find such a sequential execution that produces the same results. And if Lincheck can find such a sequential execution, then everything's fine. But if it cannot, it says, oh, there is no such execution. This execution is 100% non-linearizable. So you see, we don't even need to know the semantics of the data structure. We can simply run our concurrent code sequentially to check for linearizability. So to sum up, Lincheck takes a list of operations. It generates many concurrent scenarios, studies them, running them many times, and then automatically verifies operation results on each scenario run. That's more or less how Lincheck works. So no magic here. But let's get back to our test output. So we wrote a pretty straightforward test, and Lincheck automatically found a scenario in which our bounded queue was incorrect. And these were just 10 lines of code to detect this bug. So it's cool, isn't it? But maybe not that cool. But okay, let's say we have this output. We know that in this scenario the data structure works incorrectly, but how to analyze the error? How to understand what happened inside the implementation? Because when there are multiple threads, they can interleave in many different ways, and we don't know how exactly they interleaved. So it's still hard to analyze, to debug the detected error. And ideally, we need more data, such as an interleaving trace, including all the events, all the reads and writes, atomic operations, thread switches, all the events with the shared memory that were performed. And if we know all these events, and we have such a trace, then we can easily understand the root cause of the problem. Then we know how to reproduce the error, and we can analyze it. And that's what we did in Lincheck. We implemented a model checker to study scenario interleavings. So in the model checking mode, Lincheck fully controls the execution, tracing all the shared memory events, such as reads, writes, atomic operations, and it knows precisely where the execution switched from one thread to another. So in this case, we have the trace, and we can understand how to reproduce the error. And the only thing we need to modify is to say that instead of stress test, it should be model check and test. And if we run this test again, additionally to the scenario on which our data structure fails, we also see the execution trace with all these events that has just happened. And now we can easily understand what happened inside the implementation by following this execution trace. So I shortened the execution trace, removing the code locations, because we don't really need them on the slide. And let's try to understand the bug following this execution trace. So, of course, we also need the implementation of this offer operation, right? It's easy to understand what is happening. And let's also maintain the current state of our bounded blocking queue. So we have a queue and we have the size counter. Let's see what has happened here. So the execution starts with the second thread, and the first thing that we do is we check whether we need to insert the elements. So we read the size counter and compare it with the queue capacity. So here the size is 0, and we will not return false because 0 is less than 2, right? So we proceed. Then we add the element into the underlying queue. And then the execution switched to the first thread. So in the first thread, we call offer, which finishes successfully. It adds 1 into the queue and increments the size. And the second offer also adds 1 to the queue and also increments the size. So now you see, we have a queue, the size of which is 2, but the number of elements is not 2, it's already 3. And the reason that in the second thread, we added the element into the queue, but we haven't incremented the counter yet. And now these two offers in the first thread, they were run in between these element addition to the underlying queue and the counter increment. So we are in this state. The first thread has finished, and now we go back to the second thread and we finally increment the queue count. Now it's not 2, but already 3, and we successfully finish. So that's how we inserted 30 elements into the queue of capacity 2. So we can easily understand with this trace what went wrong. Now we can come up with some fix. Oh, we cannot, doesn't matter. But what is important is that we can easily understand the root cause of the problem. All right, so without the trace, it would be much, much harder to understand the error because typically implementations are not that simple as this one produced by ChatGPT, or and the semantics is more complex. And I work a lot on concurrent algorithms, and having such a tool was a game changer because it changed how you develop your code. But also, at JetBrains, we had a particular business reason for implementing such a functionality. So I was worked on new concurrent algorithms for coding routines. And to be honest, I was really stuck with the bugs. Because the semantics of channels is not bounded queue semantics. No, it's much more complicated. The implementation is of 1,000 or 2,000 lines of code. So it's huge. And you cannot read it and understand what went wrong. You can read it. You can explain it to many smart people, and they all will say that everything is correct. You say that it's correct, you run the test, it's not. And then you spend a week trying to understand the problem, you fix it, and it doesn't work again, and again, and again. And we needed to proceed. So at some point we decided to implement the model checker, and only after that we succeeded on designing the communication synchronization in Kotlin coroutines. And surprisingly, it also changed how we started working on developing the algorithms. So before that, when you come up with a new idea, with a new technique, usually think a lot, trying to analyze in your mind what can go wrong. You think a lot about all these corner cases and you try to find a counterexample. But when you have this tool, usually it's much easier to implement your smart idea and observe why it's incorrect. And then you improve your intuition and you can quickly adjust. You can quickly come up with a new idea and move forward. So instead of thinking a lot, you just do some simple work, you implement your idea and observe why it's incorrect. Because usually when you have an idea, you know that it's incorrect, but you don't know why.
Can you ask ChatGPT to write the test?
Which one?
ChatGPT to write the test for you.
The Lincheck test?
Yes.
Actually, no.
You should try it.
I should try. Thank you. So that's how Lincheck works. And that's cool, right? So it's 10 lines of code. You simply declare the operations, you run the magic button, and then you get very detailed instructions on how to reproduce the error. But how to analyze the trace? So what we usually do is that we read the first event in the trace, then we draw the data structure, the data structure state, then we read the next event, we update the data structure state, then the next one, and then we draw it again. So we do it over and over, and we track all these local variables in the threads. We track the data structure state. So we are doing the debugger's work. It's already cool that we can do this, that we know how to reproduce the error, but we still need to do that. But can we make the trace analysis better? Can we somehow improve it? So what we do, that we do the debugger's work. So let's do this in an intelligent idea. Let's try to make Lincheck intelligent idea friends. So intelligent idea can help us to automatically draw the data structure state and to track all these variables that we need. So for that, we recently created an intelligent idea plugin to provide native integration with the debugger for Lincheck tests. So when Lincheck test fails, we can now rerun it in the debug mode. So we have this button investigation in debug mode. So let's run it. And when we run it, so what's wrong with this? Okay. Anyway, so we have this scenario on the left. We have the current data structure state on the right. We have all the events here in the corner. And we can go forward, we can go backward, we can stop before any event. And we can stop before any event with the debugger. We can observe all the local variables, we can observe the current state, we can take a look at the data structure visualization. So this is the plugin that automates this work. And I know that some people in this room know that it helps a lot when debugging concurrent code. So that's what we recently did. And to sum up, with Lincheck, you can easily test concurrent data structures. you can do that declaratively. So uh, instead of writing how to test the data structure, you simply tell Lincheck what to test, and it does the rest. Also, Lincheck tests are very reliable. So we test concurrent implementations in coding routines in IntelliJ, in some other products, and we have no bugs. So we don't know any bugs from our users. So we detected all the possible bugs with the Lincheck. And what is also important that when we have a bug, we can easily debug it and understand the root cause of the problem. Okay. But then, so it was we have 10 minutes. We have 10 minutes. And this was a very simple example, right? So this was just some bounded queue that was developed by ChatGPT. It was very simple, it was easy to understand the error. But how does it work with the real-world code? So let's try to test the standard Java library. Who thinks it's buggy? All the JVM developers know that it's buggy. Okay, so I hope it will work. No, oh wow. So let me, do this. So, wow, a lot of errors here. Okay. So here is a test for concurrent linked DQ. Let's maybe increase the font size. Maybe a little bit more. So here's a double-ended queue. Standard class from the Java util concurrent library. So you can insert elements to both the ends of the queue, and you can extract elements from both the ends of the queue. Let's check whether it's correct or not. So who thinks it's correct? No one. Oh, whoa, one person. Two.
I want to say it's correct.
So okay, two people think that it's correct, and one more wants to believe in that. All right, let's check, right? And while the test is running, I want to say that I'm not familiar with the code. I haven't read the code. I have only the test. So it's running. It should be fine. So how many what?
In the background, how many checks it is using, how many tries it is doing.
Oh, okay. So the question is how many scenarios we try to test and how many times we run these scenarios. So this is what you can configure actually. Usually in practice we check 200 scenarios and run each of them 10,000 times. Yeah, it's usually fine.
Exhaustively generating the interleavings on
Yeah.
randomly. Exhaustively does all the combination of
So I think we need the microphone. Okay, but while we're setting up the microphone, let me show that the test output. So you see, here the Lincheck found a bug. So let's try to investigate this bug. You will be surprised. You will not understand the code, but you will understand the error. Because I did. So I think it takes 20 seconds or maybe 30 seconds, because when Lincheck finds a bug, so it generates quite big scenario, then it tries to minimize this scenario. So it's easy for you to investigate the error. So it tries to remove operations from the scenario and run the test again and again. Okay, so here we're now in the debug mode. So here we have these all these events. Oh, a lot of them, right? Here we have the current data structure state and our scenario. And what happened is that we start with the at last. So we add 1 to the right of the queue. Then poll first starts, and so it tries to extract the first element from the queue. But then the execution switches somewhere in between to the second thread. In the second thread, we add, what is 0 here? Because I don't see it. It's not mirroring. It's 0. Okay, so it adds 0 to the beginning of the queue, and it checks the last element, and the last element is 1. What it means is that this poll first, in the first thread, it should happen after pick last, right? Because if it happens before that it can't return 1. So for pick last to return 1, this 1 should be in the queue. The only way is the only sequential execution that could explain this is when at last 1 is called first, then we call add first, then we check the last element, it's 1, and then we call poll first. But poll first in this case should return 0, because the first element is 0 now. We added it in the second thread, but now it's not 0, it's 1. So this data structure in the standard Java library is incorrect. We have 2 minutes to understand why. I think it's enough. Let's try to do that. Let's try to maybe. So I think we don't need most of these. Okay, we don't need all the details, maybe. So we have this trace. So first, when we start, in the queue, we see that we have some node with no element, so the item is null. So this node is just for synchronization. This is some standard pattern. Then we add this element, and let's stop before the next operation. And we see that we have added node 2 with item 1. And we also see that head and tail, they reference the first node still, so they don't really reference the physical head and physical tail, so they're kind of oracles. So these are not, they are not important for our synchronization. But here we see that we have node 1 with no item and node 2 with the added element. So then we start poll first, and here we don't change anything. We just read the first node, we do some reads, we actually find the first node, this is node 1, but we need to find the first node with the element, so we go by the next link. So here we read the item it's null, then we go by the next to the next node, then we check the item in the next node, which is node 2. Then yes, we found the first node with the element. We check that it's still the first node. We read the previous pointer. So now we are sure that this is the first node. This is the first node, and with the element, and we're about to replace this element with null. So here if we go forward, we see that here's comparing set from 1 to null. Okay? So that's how the extractions synchronize. They try to replace item with null. If they do that successfully, they extracted the element. But if another operation comes and atomically extracts the item put in there null, then another operation has succeeded and we restart. Okay? So that's how they synchronize. But what we see here, that the first thread is about to remove the item from node 2. But then the second thread starts. So here we call at first, and let's stop after at first is finished. And here we see, oops. So here we see that this at first added node 2. It added node 3 with item 0, right? Yeah, it doesn't work perfectly for such complex structures of the visualization, but still, it's better than drawing this by hand, believe me. So this is the node that was just added. And now this is the first node. Because from this node 2, with item 1, we can go by previous link to node 1, we can go by previous link to node 3. So node 3 is the physical head of the queue. And node 2 is the physical tail of the queue. And node 1 is something in between, something useless. So when pick last checks the last node, it finds this last node, node 2, and it returns 1. And the whole first operation to extract the element, it will extract, it will update the item field in this node 2, which is now the last element, not the first one. And that's why this is incorrect. That's how it happened. So the problem is that when we check whether this node is the first node or not, then many things can change. And this node is no longer the first one. So in this case, the second thread just added another node before that. And the first thread didn't know about this. I know this is a complex example, so I think you can try to write this test to your laptop and easily investigate it, but my point is that we don't even need to read the code to understand this. We can simply read this trace, take a look at the visualization, and understand the problem. So I think this is it. Where is the presentation? Oh, here. So this is it, and thank you for attending the talk, and enjoy concurrent programming.